Welcome to qnawire.
Alright, so we have a square of length d on each side with current I flowing through it, and we want to find the magnetic field a distance x away along the x-axis. So first off, just by symmetry, we can see that the only direction the magnetic field can be in is along the x-axis. So if it had any components in the y or the z directions here, that would sort of suggest there's some preference with this loop as to which way it wants to make a magnetic field, because you could always imagine rotating the square by 90 degrees, and then the y or the z components would have to change, and that wouldn't really make any sense here. So again, just by symmetry, then it has to only be along the x direction. And so that gives us another way we can simplify things too. So each side of the square might be making a different direction of magnetic field, but overall they have to be contributing equally to the to the field along the x-axis. So to find the net field, then we can really just take the field from a single piece of the wire and then multiply it by 4, since they all have to contribute the same in the x direction. So we just want to take the x components of any one of these wires and then multiply it by 4. So again, an individual wire won't be producing just a field in the x direction. It'll have some other components, but when we take all of them, those components will cancel out. So if we just look at the x components of one, it'll end up being equivalent. So we just have to find bx for one of these. So they'll all give you the same thing, so it's really just whichever one you want to pick. So let's pick this side closest to us, and we'll kind of set up our coordinates from there. So we're going to use B sub r to find bx here. So we should have our b net then is just 4 times mu naught I over 4 pi. And then if we're doing this line here in the y direction, or the j hat direction we might call it. So let's say we're going to be at some arbitrary point here for our dl, and I'll call this dy since we're going in the y direction. So we have dy, and then that's in the j hat direction, and then we want to cross that with our r vector, and then we'd have divided by r cubed. So what's our r vector going to be here? So we're here, and a little hard to draw, but in 3 dimensions, we're going over to this point x. So we can see that in the k direction, we're always going to be right at the middle of this. So this x line is going right through the center of the square. So in the k direction, that we always have to be half the square underneath x. So always going to be d over 2 in the k direction, and then we're just going to be whatever distance up in the y direction we happen to be along this. And then same thing on the x direction. We don't know how far along the x-axis we are. We're trying to do this in general. So x and y are just variables here. But so our total r then will just be our direction, our distance in the k direction. So that's always 1/2 d. So that squared in the k hat direction. And then we have just however far we are in the y direction, and then however far we are in the x direction. So that'll be our total r. So when we do dy cross r here, all we care about is what's going to give us something in the x direction here. So all of these things will produce other components, but we know they're going to cancel out except for the x direction, so we just don't even have to worry about them. So the only component here that'll give us something in the x direction is this thing in the k hat direction here. So we just don't even have to worry about these. And so we say this is 4 mu naught I over 4 pi. And the integral, and the only one that matters for us, will be, we'll have dy, oops, and then 1/2 of d. And this is all in the k hat direction. And then, oh, whoops, this should be over r cubed here. So then we have our r, so 1/2 d squared plus y squared plus x squared, and that's all to the 3/2. And we're integrating this in the y direction, so we can call this middle point here position 0, so that we put the bottom as negative d over 2 and the top as d over 2. So d over 2 and negative d over 2. And that's looking good there. So really there's not a whole lot to do with this at this point. Pretty much we just have to evaluate this integral. And so as usual, you should just probably look this up in a table. And we do that, and we'll find then our b net is, we can get rid of those 4's, and we'll have mu naught I d over pi. So we get a d. We can pull out a d from this whole thing. And this should evaluate then to y over 1/2 d squared plus x squared, and then that whole thing times 1/2 d d squared plus x squared plus y squared. There we go, to the 1/2. And we're evaluating this from d over 2 and negative d over 2. So there's our big expression. So now we're just going to plug in our limits of integration here, and I'll just do the subtraction one step here. And we should get then after that, we'll have 2 times root 2 d squared mu naught I. And this is all in the I hat direction, since the only part of this we were keeping was, oh, this is still cross when we had dy cross k hat. So this all becomes just in the I hat direction. And this is over pi d squared plus 4x squared and d squared plus 2x squared to the 1/2. So that is b net. So that was just 4 times the x component of a single one of those lines. So the main trick of this one was really just setting it up. So it's a little bit tough of kind of thinking about through all this in 3 dimensions and getting what r will actually be here, and then recognizing we only care about the x components. So you could do this in like the complete way of integrating each one of these lines, because they will all give you different components, but then you would just find that everything cancels out except the x one. So it's going to be a lot more work. So if you can recognize right away that's the case, we can only take the x component, and so only take the cross product that gives us something in the I hat direction. So we did that, and we get this for b net. And then part B asks us if we treat x as being much, much bigger than d. So we're saying we are much farther away from the center of the square than the size of the square itself. So if we do that, what does the magnetic field reduce to? So looking here, basically then we get to ignore these d squareds in the parentheses. So when x is really large, the little contribution that adding d squared to it does is just negligible. So we say then our b is going to be 2 root 2 d squared mu naught I in the I hat direction, and then over pi, and then we just have 4x squared times 2x squared to the 1/2, so just root 2x. And it looks like then we can cancel that root 2, and that's 2 and that 4 will be just a 2. And so this should be d squared mu naught I in the I hat direction, pi, and we have x cubed, and then we have a 2 out front. So that's our magnetic field. And then they ask us what the dipole moment of this would be. So comparing this with where they talked about that in this chapter, so chapter 28 and then section 7b, if we compare this to the expression they derive, we can see then that the dipole moment should be d squared I in the I hat direction.